Okay, so it's like 7 o'clock in the morning, still waking up a little bit. So if I say anything that doesn't make sense, not my fault. So let's get to it. These first four are graphing. The first two are exponential graphs. The second two are logarithmic graphs. You'll see some similarities in how they're graphed. For the first two, the exponential graphs, we need to do three things. First thing is to find the horizontal asymptote. Second thing is to find the y-intercept. Third thing, plot points. Okay. So the horizontal asymptote is found by vertical shifts in these functions. Vertical shifts are transformations that occur outside the function. So this -1 moves the horizontal asymptote down 1 unit. And then we do this one at the same time. So we compare the two graphs. This +2 on the outside of the function moves the vertical asymptote up 2 units. Okay. Now the y-intercept is found by letting x equal 0. So if this x right here equals 0, 0 minus 1 is -1. 3 to the -1 minus 1 is -2/3, which is about right there. And then over here, 0 plus 1 is 1. 1/4 to the power of 1 is 1/4. 1/4 plus 2 is 2 1/4. So that's just slightly above 2, right about there. Third thing we need to do is plot points. Now, what that really means is we're going to make an XY table for both. Now you can fill in the x column with whatever numbers you like, but it really depends on what type of exponential function we're graphing. In number 1, since the base right here is larger than 1, that means this is a growth function. So moving from left to right, the graph kind of skims along the horizontal asymptote and then increases very rapidly. So if we choose x values that are negative over here, the y values we're going to get are just very small decimals. If we choose x values that are positive, we're going to get the integer values of y. I'm going to choose x equals 1 and x equals 2. And on the other hand, over here on question number 2, the base 1/4 makes this an exponential decay graph. So if I chose positive values of x, I'm going to be getting very, very small values of y. But if I choose negative numbers like -1 and -2, I'm going to be getting easier values of y to graph. They'll be up here somewhere. So I'm going to choose -1 and -2. Okay, so back to here. If x equals 1, 1 minus 1 is 0. 3 to the 0 minus 1 is 0. So 1, 0 is on the graph. If I let x equal 2, 2 minus 1 is 1. So we have 3 to the 1 minus 1, which is 2. So the graph looks something like that. Over here, if x equals -1, we have -1 plus 1. So we have 1/4 to the 0 plus 2, which is 3. So we have -1, 3. And then if x equals -2, -2 plus 1 is -1. So we have 1/4 to -1 plus 2, which is 6. So -2 plus 6. So the graph looks something like that. Now, for logarithm graphs, there's similar steps as these three steps. It's just everything is its inverse. Instead of finding a horizontal asymptote, we're finding a vertical asymptote. We're going to find an x-intercept, and we're going to plot points, but it's going to be in a different way. So for logarithm graphs, since we're finding a vertical asymptotes are affected by horizontal movements to the left or to the right, so we look inside the function for those. Inside the function is opposite. X minus 1 means there's a transformation to the right. So our vertical asymptote is right there. Our x-intercept is found by letting y, or in this case f of x, equal 0. So we solve the equation 0 equals a log base 4 x minus 1 plus 1. If we subtract 1 on both sides, we get negative 1 equals log base 4 of x minus 1. We write this in exponential form. This is our base, 4. Our exponent is negative 1, so 4 to the negative 1 equals x minus 1. 4 to the negative 1 is 1/4. And then if we add 1 to both sides, we get 1 1/4 for x. So that's just barely beyond, slightly beyond 1 right there. Now, we still make an xy chart, but with logarithms specifically, rather than filling in the x column, it'd be easier to fill in the y column and then see what values of x produce those y values. So if we let f of x equal 1, and then we solve this equation, subtracting 1 on both sides, we get 0 equals a log base 4, x minus 1, 4 to the 0 equals x minus 1. 4 to the 0 is 1. Then if we add 1 to both sides, we get 2. So 2 comma 1 is on the graph. And if we repeat this process and let y equal 2 this time, then if we subtract 1, this is going to equal 1. Then over here we have 4 to the 1, which is 4. Then if we add 1 to both sides, we get 5. So 5 comma 2 is on the graph. And over here, it can be a very similar thing. The vertical asymptote has been affected by this transformation to the left, negative 4. And then we find the x-intercept by letting f of x equal 0. So 0 equals log base 2. If we subtract 1 on both sides, we get negative 1. Writing this in exponential form, we have 2 to the negative 1. It's x plus 4. 2 to the negative 1 is 1/2. If we subtract 4 from 1/2, we get negative 3.5 for our x-intercept. Now, make a little xy chart. Y equals 1 this time, and we subtract 1, we get to 0. 2 to the 0 equals x plus 4. 2 to the 0 is 1. And if we subtract 4, we get negative 3. So negative 3 comma 1. And then if y equals 2, and we subtract 1, we get a 1. 2 to the 1 is 2, and if we subtract 4, we get negative 2 for x. So negative 2 and there's the graph, the graphing section. Okay. Next section is probably the easiest section on the test. It's just rewriting each equation in exponential form. the exponential has to have the same base as the logarithm. So since this has a base of 6, we're going to use a base of 6. This is our exponent, 6 to the third. Equals 216 over here. Our base is 9, so it's 9. This is our exponent squared. Equals 81. Over here, 13 to the 0. 1. And over here, natural log has a base of e. So this is e to the x. Equals 155. For page 2, we're rewriting each in logarithmic form. Our logarithms have to have the same base as the exponential. This has a base of 2, so our logarithm has a base of 2. Log base 2 of 64 equals 6. Now if you forget, especially on this when you're going from exponential form into logarithmic form, if you forget which numbers go where, what we're trying to do when rewriting in logarithmic form is to get rid of the base so that this exponent is no longer an exponent. So what kind of a logarithm cancels a base of 2? It's a log base 2. And then over here we would take a log base 2. So those would cancel out. So we have 6 equals the log base 2 of 64. You can think about it that way as well. Over here we have a base of e, which means we have to use a logarithm that has a base of e. That's the natural log. 216 equals x. Over here we have a base of 289, so we need to use a log of base 289 of 17, 1/2. And again here we have a log base 8 of 4 equal to 2/3. Now we're evaluating each expression for this section. One of the properties we learned is anytime you take the logarithm, regardless of the base, if you take the logarithm of 1, that always equals 0. Every time. Anytime you take the logarithm of 1, it equals 0. Over here, log base 16 of 4. Now, the property we learned regarding logarithms is if the logarithm has the same base as what's inside the logarithm, then those bases cancel out. So what we need to try to figure out is how to rewrite 4 as something that has a base of 16, and it's the same as 16 to the 1/2 power. 1/2 power means square root, and the square root of 16 is 4, so these are equivalent. And the important thing is now they have the same base. Log base 16 cancels with the base of 16, leaving 1/2. For here, it's a little bit easier to see that we can get matching bases. Log base 5, 125 is the same as 5 to the 3rd power. So those cancel, leaving 3. Over here, 16 is very similar to 14. We need to rewrite 5 to have a base of 25. 5 is 25 to the 1/2. Those end up canceling. So this equals 1/2. Now over here, if you have a base of 3 and then as an exponent you have a log with a base of 3, those are inverse functions. They cancel each other out. So we have what's left over is 8. And then over here, natural log has a base of e. So the natural log is the inverse of the natural exponential number, or the natural number. So what's left over is 5. Okay, now we have a section on expanding and condensing. So on number 19, we're condensing into a single logarithm, which means these two logarithms have to be written as one logarithmic expression. First thing we need to check is, do they have the same base? They do. Okay. Now, when you're condensing, you start with a power property, which means any numbers in front of logarithms need to move back up as exponents inside the logarithm function. So we're going to take this 3 and this 15 and move them back up as exponents first of all. So we have the log base 5 of u to the third minus log base 5 of v to the 15th. Now we look at what separates the two logarithms. A subtraction sign means that this is the quotient property. So when we condense these two logarithms into a single logarithm, we need to form a quotient now with these values, u to the third over v to the 15th. And this one's going to be very similar to number 20. First thing we do is the power property, moving these numbers in front of the logarithm back up as exponents. We have log base 5 of x to the 36 plus log base 5 of v to the 6th. Now we have a plus sign separating the two logarithms. So when these condense into a single logarithm, we have to form a product now of x to the 36. That's actually a y, not a v, times y to the 6th. Expanding is the exact opposite. We're not going to start with the power property. That's only with condensing. With expanding, we start by either expanding the quotient, or in this case, over here in 22, expanding the product. So since this forms a quotient, we're going to expand this using a subtraction sign between the two logarithms. So this is going to be log base 5 of u squared minus log base 5 of v squared. And then we end with a power property. These powers need to move down to front of the logarithms. 2 times the log base 5 of u minus 2 times the log base 5 of v. Now here in 22, there's 3 terms that are forming a product, which means we're going to end up with 3 logarithms, all separated by a plus sign. We have the log base 4 of u plus log base 4 of v plus, now I'm going to move this power down here just to save time, plus 3 times the log base 4 of w. Here, these again are forming a product. Product means multiply. So we're going to separate these. Now we're only going to have 2 logarithms because we only have 2 terms inside. Log base 8 x to the 5th plus log base 8. Now we end with the power property. The powers, the 5 and the 2 move down in front. 5. So log base 8 x plus 2 times the log base 8 of y. Okay, this one here, number 24, is going to be a little bit more involved. Overall, we have a quotient. Now there's a product inside of the quotient, but the first thing we need to deal with is expanding this quotient. So we're going to have a subtraction sign between 2 logarithms. We're going to have the log base 4 of the numerator, a to the 6th, minus the log base 4 of the denominator. And now we take a look at this one here. This logarithm has a product. So we need to expand this product, but we need to be very careful. Right now we're subtracting the log base 4 of the product c times b to the third. So we need to make sure that when we expand this logarithm that we're still subtracting the entire thing. The way we do that is using parentheses. Log base 4 of a, I'm actually going to move this 6 down to the front, so it's 6 times the log base 4 of a minus, since we're expanding this, but we need to still subtract the entire expression, this is going to be the log base 4 of c plus the log base 4 of b to the third. These parentheses are very important so that we subtract the entire expansion. And now we need to distribute this negative sign. So we have 6 times the log base 4 of a minus the log base 4 of c minus, I'm going to move this 3 down to the front of the logarithm, 3 times the log base 4 of b. Now we're to the section on solving equations, both logarithmic and exponential. It's pretty much the same 3 steps for either type of equation. We're starting with logarithmic. First step is to isolate the logarithmic term, which is this term right here, log base 2 of v minus 7. So the negative 3 in front is multiplying the logarithm. So the inverse of multiplying is dividing. So we divide by negative 3. We have the log base 2 of v minus 7 equals 3. Once the logarithmic term is isolated, we need to rewrite this in exponential form using a base of 2, a power of 3, Now, since the variable is no longer inside of a logarithmic function, we can solve now easily by adding 7. 2 to the third is 8. 8 plus 7 is 15. Now over here, this is the logarithmic term right here, natural log of x minus 1. There's nothing in front of it. There's nothing behind outside of the function, so it is already isolated, which means we can go straight into exponential form. Remember, the natural log has a base of e. So in exponential form, this is e with a power of 3 equals x minus 1. Adding 1 to both sides, we have e to the third plus 1 equals x. Since we don't use calculators, we leave it as e to the third plus 1.